This is a lecture for Math 202 Calculus 3, Chapter 1, and it is on the quadratic surfaces, which are also called quadric surfaces. This is a very basic lecture on these surfaces. It's much better to look at lots of pictures in the book or on the internet, and I'll try to show you some of those pictures in a few minutes. So basically, you have in the homework and in other places, you're encountered with some kind of equation for these surfaces, and you have to put it into the standard form. The standard forms are all listed in Stewart and also in Thomas. For example, here's the standard form for the ellipsoid. X squared over a squared plus y squared over b squared plus c squared over z squared equals 1. There's the standard form. Now, if you're given something like this, it's obvious. You can identify that as an ellipsoid right away, where a is 6, b is 3, and c is 12. Now, sometimes things are written a little bit differently, and that throws some people off. Okay, for example, it could be written like this: x squared plus 4y squared plus 9z squared equals 1. All you have to do is put the 4 in the denominator as a 1/4 and the 9 in the denominator as a 1/9, and then you'll have the standard form. So a squared equals 1, b squared equals 0.25, and c squared will equal 0.11. Okay, so it's just a little bit of a fooler when you first look at it. But notice you've got an x squared, y squared, z squared all added together, and some coefficients that you can rewrite into denominators. With these quadratic surfaces, the lines, the meshes that you would draw on them in the horizontal plane and in the vertical plane are called traces. They look like a wire frame. In fact, if you draw those, enough of those traces and connect up the lines, you can then draw the whole surface. When you take the horizontal traces and you project them down onto the plane, into 2D projection, those are called contours. So you only have contours of the horizontal traces. Those contours are what you get on when you look at an elevation map, for example. Now, starting with the basic equation, there's ways to find the form of the traces, the form of the equations for the traces, give them a name, and that's exactly how these quadric surfaces got their names in the first place. Okay, so for the horizontal traces, these are planes that are parallel to the xy coordinate plane. These are horizontal planes, and in each of these horizontal planes, z is constant. So when you go back to the original equation, you make z equal alpha or some constant, and then you rearrange and see what you get. For the vertical traces, you have two planes. Planes parallel to the xz plane. In those cases, y is a constant. And then you also have the planes parallel to the yz plane. In this case, x is a constant. So you see, whichever coordinate is left out of the plane, that one is a constant. So here's an example of that. Say you had an ellipse, and you want ellipsoid, and you want to find the horizontal traces. On the horizontal traces, z is a constant, so set z equal to alpha and put it in the equation. So that's what I did right here. Then rearrange and see what you get. To rearrange, I could put all the constants on one side, so that's sitting out here. On the other side, I have x squared over a squared plus y squared over b squared equals a constant. Well, I could divide that constant out, and after I divide it out, the right-hand side would equal 1, and that would be in the standard form for an ellipse. That's how you identify those traces as ellipses. Set one of the coordinates equal to alpha, equal to a constant, and rearrange. Okay, here is an ellipsoid, picture of it on the internet, and I can rotate this figure around, and you can see that the horizontal traces, well, if we set this right, the horizontal traces here would be in white. So I'll look at them, I'll look down on them, and you can see those are ellipses. Actually, it turns out that the ones in the vertical planes, the green one, and also the kind of pinkish colored one, red, I guess it's a red color, those are also ellipses. You see how they make up sort of a wire frame. There's additional lines on there, those are also, well, the ones that are coming through like this at an angle, those are not traces. The traces have to be parallel to the axis. So others, let me see if I could draw some. This is a plane, it's probably the YZ plane. So if I looked out on the figure, I would see another ellipse. It's not going to work very well, is it? Well, maybe it is if I straighten the thing up, which I can't seem to do. All right, so I'll have to do it by hand. At any rate, if you traced more ellipses on here, more traces, these are all parallel to the YZ plane. And they will all be ellipses, so they aren't really a wireframe. This is a better figure for showing ellipses. This is your elliptic hyperboloid. The horizontal traces are ellipses. That's here in white, although it looks more like a circle. You can see as you go up in this, it could be, well, it could be circular, but it's going to be an ellipse. Right now, well, a circle is a form of an ellipse. Okay. If I look in one of the vertical planes, I see a parabola. If I look in the other vertical plane, I see a parabola. Now you see parabolas throughout. It's kind of hard to see it, but you can see these wire lines, which I can't draw enough to trace. But you can see one here. This is an ellipse. This one's an ellipse. This one's an ellipse. So as you go down this figure, you would have a family of, a family of parabolas. And as you go up, you'll actually have a family of ellipses. They'll be getting bigger and bigger as you go up in this figure. So the horizontal traces are ellipses, the vertical traces are parabolas, and that's where this surface got its name. This is a hyperbolic paraboloid. It's studied quite a bit in Calculus 3, and the reason for that is you can see these parabolas here, vertical parabolas, this kind of the pink colored one here, and the green colored one, that's a parabola, and they're in different coordinate planes. Let me see if I can turn it around for you. It's kind of tricky to turn it around. Okay, so those are parabolas. In the other directions, if I look straight down on it, now you see a hyperbola. Actually, there's two hyperbolas. There's one that's drawn on this figure, and there's another one that's coming through like this, that's going in the other direction. These would be a family. If you start drawing all of them, you would have a family of hyperbolas. Now I've listed here again the equations just for the ellipsoid, the elliptic paraboloid, the hyperbolic paraboloid, and the cone. Now you'll see these equations in several different parts of the book, and you'll think, well, this was the equation for it, and now they want to present it in a different way. They want to present it as a parametric equation, or they'll want to present it as some kind of a function. And the reason you keep seeing them is some of them can be rewritten, and the one that can really, these two can be rewritten easily as functions, because you see the z is isolated. All right, so I could write this as some function of x and y equals, and I could put the c over here, cx squared over a squared, I'm going to run out of room, plus cy squared over b squared. So this can be written as a function. This one can also be written as a function because the z is isolated. So in both of these cases, I have some function f which takes two variables x, y and maps them into z. So in general, this f is mapping r2, see two variables here, into a single variable r1. If you looked at the graphs, you could see why those would be functions, whereas the others would not. But that's why these get identified and broken out as functions, and then you don't see the equation for the ellipsoid and the cone and the others. Can the ellipsoid be written as a function? Well, it can't, because even though even though I isolated the z squared, so maybe I write z squared over c squared equals 1 minus x squared over a squared. Actually, this would be a negative, and this would be a positive, plus y squared over b squared. I could isolate it like that. I could even multiply through by the c squared. But when I go to take the square root, I would have z equals plus minus the square root of a bunch of stuff. So for each value of x and y, I do not have a single value of z. Remember, for a function in two variables, if you have, for a function f of x, an equation is a function if for each x there's only one y. In this case, for each pair x, y, there can only be one z. In this case, that's not true, so this is not a function. Whereas in this case, it is true. For each value of x and y, I get only one z. Similarly, for each value of x and y, I get only one z. And that's why they can be written as functions, whereas the others cannot. There was a question in the homework on rewriting the equations in cylindrical coordinates. To do that, just substitute for r, x, r cosine theta, and for y, r sine theta. Z, of course, stays the same in cylindrical coordinates. So for example, for elliptic paraboloid, you could replace the x by r squared cosine squared theta because there was an x squared term. Here's your y squared term, and rearrange a little bit. The hyperbolic paraboloid also could be written easily in cylindrical coordinates. Now I'll go through a little bit of an example here on finding those traces. So I'll start with the equation for the hyperbolic paraboloid. Z over c equals a squared, x squared over a squared, minus y squared over b squared. Right. The vertical traces of parabolas. Here's a general form for parabolas. X squared equals 4p times z plus k. This would be in the xz plane. Here is one in the yz plane. Y squared equals 4pz plus k. Of course, the p and k are going to be different in either of those equations, but I was just trying to show the standard form. So to find the vertical traces in the xz plane, or parallel to the xz plane, or xz, that's a y, xz plane, set y equal to alpha and put it in the equation. When you put it in the equation, you get this. I just substituted for y, I substituted alpha. Then rearrange. I can break out the x squared, and now you can see here that this is in the standard form for parabola. To get the vertical traces in the yz plane, I set x equal to some constant, put it in the equation, then rearrange it, and again you get an equation for a parabola. Now for the horizontal traces, that would be traces in the in planes parallel to the xy plane, xy coordinate plane. You set z equal to alpha and put it in the equation. So here's z is set equal to alpha. It doesn't take much rearranging. All you have to do is divide by alpha, multiply by c over alpha, and you'll get a 1 here. Now, if z is greater than 0, you'll get the negative sign in here as was written in this case. If z is less than 0, the negative sign will end up being out here. This will become positive. And that's how you get that set of parabolas, the set of hyperbolas for this hyperbolic paraboloid. It had kind of a saddle point here, or it does have a saddle point here. Well, in this region, the hyperbolas are going like this. The direction of the hyperbolas has to do with these signs. Down here in this region, the hyperbolas will be going like this. And it's the same on the other side. So when you put it down into a plane, you will see a set of hyperbolas, so different branches, in one direction, and then you see hyperbolas in the other direction. Now these are paired. Some of them have to do with where the saddle is. This is z equals 0 line. The xy axis has to do with the upper part of the saddle, and these have to do with the part of the saddle that would be by the horse. And here are graphs of this hyperbolic paraboloid, and it's sort of color-coded. If you look in the lecture notes, you can see the scale for the color coding, but you can see barely that there's hyperbolas here in this plane and hyperbolas here in this plane. These are opening in this direction, and the other hyperbolas are opening in this direction. So when you look over here, of course, this is rotated now. This direction is actually this direction. You can see the red ones over here, and you can see the blue ones this way. All right. The blue ones came from this part of the saddle, and these red ones came from this part of the saddle, the upper part of the saddle. So these are called the contour lines because they're 2D projection of the traces. Over here they're called traces, and these would happen to be the horizontal traces are shown. So the horizontal traces are hyperbolas. The vertical traces are parabolas, and you can't really, might not be able to appreciate that right here. It's pretty hard. You can see a parabola here, and then sort of look in this direction. This is also a parabola here.